Hello, my name is Cindy, and today I will be explaining microtubule structures and how they are formed. So before I get started on their structure formation, I just want to give you guys a little bit of background of what exactly microtubules are. They are the largest structural element of the cytoskeleton in eukaryotes. They're primarily composed of a protein called tubulin, and they are generally involved in the movement of components inside of the cell or outside of the cell. There are two groups of microtubules, cytosolic microtubules and axonema microtubules. Cytosolic microtubules form meiotic and meiotic spindles in the cells, which are required for chromosomal movement during meiosis or mitosis. They also contribute to the special disposition and directional movement of organelles in the cell. Basically, they organize fibers that help guide these organelles to their destinations. Axonema microtubules are highly organized and are involved in cellular movement, so they help structure cilia, flagella, and the basal bodies. So what makes up microtubules? They are made up of two monomers, alpha tubulin and a beta tubulin. These monomers come together and form a heterodimer known as alpha-beta tubulin, which then comes together and forms a linear polymer known as protofilaments. Microtubules have a plus and a minus end, making them a polarized structure, and microtubules can form by themselves, which they are known as singlets, or they can form in groups, which they are then named doublets and triplets depending on how many microtubules are attached to each other. Here I provided an image that gives you guys a little bit more details on the singlets, doublets, and triplets. Something that I should point out on the arrangement of these microtubules, they are all going to be, or I should say the singlets are going to be composed of 13 protofilaments in a circle, or that make up a tube. As you add more of the microtubules to make the doublets, and the triplets, they have one complete 13 formation, I guess, and then the secondary and third structures are going to have only 10 protofilaments. So here I'm going to explain how a microtubule is formed. They are formed by reverse polymerization of the tubulin dimers. Oligomers form when clusters of tubulin dimers aggregate together and begin the process of nucleation, or the bringing together of the oligomers. Once nucleation is completed, the microtubule starts to grow in a process known as elongation, which is where the subunits are added to each end of the microtubule. Finally, the concentration of free tubulin becomes limited, and this is where the plateau phase begins, which is the process of assembly and disassembly of the microtubule. Here I give a little bit more detail on how the microtubule grows. So critical concentration is when the tubulin heterodimer concentration at the microtubule assembly is balanced with its disassembly. So then critical concentration determines the growth rate of either end of the microtubule. Critical concentration on the plus end is generally lower than the minus end, so then microtubule assembly is more rapid on the plus end than on the minus end. If free tubulin concentration is higher than the critical concentration on the plus end, however, but lower than the critical concentration on the minus end, assembly occurs on the plus end, and then the disassembly occurs on the minus end. This simultaneous assembly and disassembly of the microtubule is known as treadmilling. What ends up happening in treadmilling is that the tubulin molecules at the plus end is displaced progressively over time along the microtubule, and it is then eventually lost by depolymerization at its opposite end. And finally, I'm going to explain some of the roles of microtubule-associated proteins, or MAPs. Um, there are many different types of MAPs. MAPs are regulatory proteins that can bind to microtubules that allows for interactions with other filaments and cell structures. I've listed a few here, which are the tau protein, MAP2 proteins, plus minus tip proteins, and catastrophins. Tau proteins cause microtubules to form tight bundles in the axons of nerve cells. MAP2 proteins have a similar role like tau, but they formed a less densely packed bundle. Plus minus tip proteins play a role in stabilizing the microtubule, which here I have an example of the EB1 protein that helps decrease the loss of subunits in the microtubule. And then catastrophins do the opposite of plus minus tip proteins, where they actually promote depolymerization, which can help control, or which can help cells control when and where microtubules can form and depolymerize. Thank you so much for listening to my presentation, and I'll see you guys in the next one.